What's up everyone? Welcome to your first grade 8 science video lesson. Today we're going to go over 3 big things that are important to mechanical systems and physics in general. We're going to be looking at mechanical advantage and how that helps everything and everyone in life, from the pyramid builders to you trying to get something from under the couch. Sometimes I have to get cat toys from under the couch, and I actually use mechanical advantage to help me solve that without hurting my back. The second thing we're going to look at today is work. What I mean by work, not just going to work, not just classroom work, not homework, but actual work regarding moving something. Like, what is work? We're going to delve into that this lesson. And also we are going to end it on efficiency. So what is efficiency? How to calculate efficiency? And just all around why it's important for us as human beings to be efficient. Okay? At the end of this lesson, I'm going to explain your assignment for this week, because you do have an assignment, but I was nice enough to give you 2 options. You have option 1, which is a computer-based assignment where you can do it in the simulation link that I give you. And then the second option is that you can make or design your own catapult or mousetrap car. All the instructions will be there for you in the assignment folder that I give to you. You're going to have 2 files attached to this video. One is going to be option 1 and one's going to be option 2. Now, the end of the assignments are different, but you all are going to have same amount of questions regarding the stuff before the assignment. So what you need to do for this lesson is complete those questions and complete whatever option you decide to do. Remember, you don't have to do both. Just one, okay? So pick one from the attachments. Without further ado, we're going to get the lesson started. Okay, so we have the lever, and we want to calculate how much easier it actually is than just lifting it normally. So we want to calculate the mechanical advantage. Now we can here go load force divided by effort force. So the effort force meaning how much effort you're putting into lifting that object, and the load force is how heavy that object is. So let's do the simulation as an example here. So you have your load force, let's say is the garbage can, and that is going to be 10 kilograms. Now when you lifted it, you used 5 kilograms of force. That's the fire extinguisher. So divided by 5 kilograms. So what does 10 divided by 5 equal? 2. So it is 2 times easier using this method, okay? Or again, what you could do is you could go length of the effort arm divided by length of the load arm. So the effort arm, let's look at it. It is 8, let's say feet, okay? And if we divide that by the length of the load arm, in order to lift that garbage can, we had to move the garbage can to 4 feet near the fulcrum. So divided by 4 kilograms equals, you guessed it, 2. So 2 times easier. That is a way you can calculate mechanical advantage. Okay? Now when you're, let's say, in an argument of what's easier, right? You can do this as evidence. So for these examples, you lifted 50 newtons with 5 efforts, with 5 newtons of force. How much easier it is? Well, the load force is 50, and you divide it by 5, which is how much force you're putting on it. So the mechanical advantage is 10. It's 10 times easier than if you were just to try to lift it by yourself, because you need the exact same newtons in order to lift it without a machine. Now let's say you're trying to lift the same thing, but you changed where you're lifting it from. So you changed the size of the lever, and now you're putting 15 newtons of force in order to lift it. What's the advantage of that? Well, if you go 50, because it's the same amount of force, divided by 15 newtons, because that's how you're tripling how much you have to use, how much force you have to use to lift it. The mechanical advantage is only 3.3, so it's 3.3 times as easy as lifting it just normally. So which lever, in this case, on these 2 examples, which lever makes it easier? Yeah, correct. It's the first one because 10 times is a lot easier than 3 times. But they're still easier than just lifting it, you know, vanilla. So work happens when you move something after exerting force on the object. All right. So for example, you see a guy here, he's pushing the wall, okay? And he's pushing really hard on it, but it's not moving, okay? He's still pushing a lot of force on it, okay? But the wall ain't moving. It's gonna stay still. It's stubborn wall, all right? Now, this is because the force shooting back at him is the same as the force he's exerting, and no distance is happening, so he's not moving it, so there's no work being done, all right, even though he's putting in the effort. Okay, now for this image right here, for example, you're pulling a wagon full of sunflowers or any type of flowers, or I don't know, sunflowers different colors. Is there some genetic GMO manipulation that causes sunflowers to be pink and red? Did they happen naturally? I have no idea. Anyway, the little boy is pulling the wagon and the wagon moves. Work is being done. So he's using force to pull the wagon and the wagon is moving. So the newtons of force that he's using to pull the wagon is actually moving the wagon. So work is being done. That's when you know it's being done, okay? This could actually be analogized to studying, right? You could look at your notes all day, right? You could like stare at your notes for 1,000 years. I gotta study. But we all know that just staring at your notes isn't going to benefit you in terms of memorizing or learning. So you're still putting the effort, but the work, like the whole studying thing, isn't actually happening. So don't waste your time. Please rewrite your notes, practice, talk to someone, learn your flashcards, manipulate the information given to you in different ways. That's how you're going to learn science. Okay? Work equals force times distance. I'm going to tell you that work, let's go here, units. So for work equals joules. And that's the unit we use for work. For here we go for force. The unit is newtons. Okay. And distance, we are going to use m for meters. Now this is very important that you get this right, because a common mistake that I'm going to see from a lot of you, I might, who knows, prove me wrong, is that I'm going to give you, like, let's say a question, Timmy moves an object that weighs 50 newtons and he moves it 2 kilometers. How much work did he put in? Well, if you just went 50 times 2, you're going to get the wrong answer, because 2 kilometers is actually 2,000 meters. So please make sure you get the units proper. Write it down if you have to, memorize it, do that, okay? So an example we have here is a student pushes on a box with a force of 20 newtons. So 20 newtons of force and a distance of 10 meters. How much work does a student do? Okay, so make this an equation, right? So force times distance equals work. How much force? 20 times how much distance? 10 equals W. So we can all do the math here. 20 times 10 is 200. So he actually does work equals 200 joules. Okay? Get used to rearranging these equations here. Okay? So for this, I'm going to walk you through it here. For this question, for the first question, you're going to go fill in the blanks, force times distance. So for here, they give you the amount of work, and they give you how much it's moved. Now you got to calculate the actual force. All right? So what's a way to do this? Well, you got to rearrange the equation. So we'll go here. So we have, let's do that equation again. So force times distance equals work. Now you have, so you don't have force, but you have the distance. It's 1 meter equals 200. So how would you rearrange this question to figure out F? So what you would do here is you would go work divided by distance equals force. All right? So the way we would do that is go 200 divided by 1 equals 200 newtons. Now, how can we double check that? If we plug in what our answer was to our original equation, force times distance equals work, we can go force is 200 because that's what we got, times distance, which is 1 meter, equals work, and the work will equal 200 joules. So the method for figuring this out, do what I just did here and then double check your answer to see if it works when you, because if you have all the variables, you're going to see if it works, right? So do that, please. Other than that, for this assignment, there's a bunch of word problems, but what I want you to do is I want you to try to distinguish the variables on all this. So in each case above, work done has been the same, 100 joules. However, the amount of force needed to do the work has changed. The easiest way to do work was in example letter because. So basically this is telling you, asking you to tell me why one of these is easier than the rest, basically. Okay? So there's a bunch of word problems and it's just basically using these 3 variables. Okay? It's using force, distance, and weight. Okay? Now, alright everyone, I just want to go through one of the examples here for work before we move on. Number 3 here in your workbook is Vivian and Christy were having a tug of war with the gym teacher. The distance to pull was 3 meters. They pulled as hard as they could, but they could not move him. Assuming the teacher mass is 90 kilograms and Vivian and Christy pulled with a force of 800 newtons, how much work did they do? Show your calculations. Now, the main thing we want to work here to look at, because this is where people are going to mistake, is the mass of the teacher isn't in newtons, it's in kilograms. Now we got to convert, in order to make the equation work, we got to convert kilograms to newtons. Now 1 newton, okay, 1 newton is equal to 100 grams, okay? So that is shown right here, okay? 1 newton is approximately 100 grams. Now, with that being said, how much grams are in a kilogram? So 1 kilogram equals 1,000 grams, okay? Because kilo, 1,000. Think of kilometer is 1,000 meters, a kilometer, okay? A kilogram is 1,000 grams. So how many newtons would be in 1 kilogram? So 1 kilogram also equals 10 newtons, okay? So for our question here, we have our gym teacher who weighs 90 kilograms. How much newtons is that? So if 1 kilogram weighs is equal to 10 newtons, how much is 90 kilograms in newtons? We want to multiply this number by 90. So 10 times 90 equals, you guessed it, 900 newtons of force. So boom, now you can calculate this. So this is a lot easier now because instead of the teacher weighs 90 kilograms, what it's actually saying is the teacher is exerting 900 newtons of force. Okay guys, we have to back up just a second here, okay? Think about the wording of the question. Now the goal of the students was to move the teacher 3 meters. Now if we look back at the question, it says that they didn't move the teacher at all. Vivian and Christy were having a tug of war with the gym teacher. The distance to pull was 3 meters. They pulled as hard as they could, but they could not move him.
As hard as they could, but they could not move him.
And what is one of the requirements for work to be done? Well, it has to move something. Think back to what we said earlier in this lesson. So if the distance moved is 0, that means work being done also equals 0, because anything times 0 is 0. So we got to look back at this. So the force produced, whatever times 0 is going to be 0. So regardless of all the calculations we just did, we know that this is going to be 0. Showing our work like this is important because other questions are actually going to have work produced. So it is important that we practice what we just did by converting kilograms or any sort of other unit into newtons, and just converting all the units we're given into units that work with our equation. So that's force in newtons, that's distance in meters, and that is work in joules. So if we get any other units in these questions, we know that we have to convert them in order to get the right answer. Now, as you're going through the other questions, I want you to make sure that you read it carefully and do the work, do the conversions, because it's good practice, but make sure you read it carefully, because this could be an easy mark off any sort of assignment where the final answer is going to be 0. So now that we got the idea of calculating work and calculating mechanical advantage, we're going to go over calculating efficiency. So how efficient is something? I think we all understand what that word means, meaning that optimization, doing something the easiest way possible, all right? And there is a way that we calculate efficiency, all right? So let's go here. Energy, friction, and efficiency. That's our third topic today. Now, the thing I want to go through here just as some extra knowledge here is kinetic energy. Does anyone know what kinetic energy is? Think of the word kinetic. Kinetic is also another word for like movement or the relationships between things, okay? So kinetic energy is energy in motion, okay? It is generated by something moving. It can be movement of particles, a ball, a swing, a person's arm. It's like a hockey stick. It can be that type of energy.
Energy in motion.
Okay? Potential energy is that is when energy is stored and it could be released at any moment. Now this is actually important on job sites, because if things have potential energy, as soon as you move something that disinhibits or makes that energy available, then it becomes dangerous, okay? So think of like a spring. If you crush a spring, if you shrink a string, as soon as my hands release it, that energy pushes out. Elastic bands have potential energy, because as soon as you let it go, energy, right? Springs, as soon as you let it go, energy. Chemical bonds, once you get into chemistry, that is potential energy, because as soon as that bond breaks, energy. Atomic bombs, guys. All right? An object above the ground. So in the workforce, if you ever work in any sort of industrial setting, potential energy is a big, big thing, okay? So think of something hanging off a crane, okay? That force has the potential energy of hurting someone, because as soon as you release it, it can fall down, and that energy is going to be pushed. Or think of something on a hill. Let's say you roll a ball up a hill and you're holding the ball there. As soon as you let go of the ball will roll down, because that ball has potential energy at that point. Okay? So there's a bunch of links there. I want you to look at some kinetic and potential energy. So in short, potential energy is attributed to mass and position. So how things are, how heavy something is, so how much newtons it has, and where it is can dictate if it's going to roll down. It has a lot to do with gravity. Kinetic energy is the association with mass and speed. So that's you deliberately using energy to move something. So think of it as like passive and then deliberate. Okay? Now let's get into efficiency, everyone. Efficiency is a ratio that tells you how much energy you give to the machine was transferred to the load of the machine. You have a light bulb, okay? We're talking about efficiency here, okay? And what the goal of a light bulb is to have all the energy you give to it turn into light, because that's the goal. Now, unfortunately, the goal doesn't always come to pass, right? Most of the energy of a light bulb, of like a regular incandescent light bulb, is given off as heat. About 95% of all the energy given to a light bulb is heat, and only 5% of that is light. Now, it would be awesome if 100% of that energy turned into light, because then it would not give off heat at all. It would be a cold light bulb. The calculation for efficiency, if you really want to get into it, is work output divided by work input times 100. Okay, that is a calculation. You can prove it, evidence-based, if something's efficient. Okay, so the work output of a light bulb is how much light it gives off, how much energy turns into light. And the work input is how much of total energy is coming from the outlet or the battery or whatever energy source you have for it. So an example, the example we have here, we have a certain light bulb, okay? And this light bulb, great light bulb, tremendously great, best light bulb ever. Consumes 200 joules of electrical energy per second. 200 joules of energy per second, okay? Think about that. But only emits 25 joules of light per second. Calculate the efficiency of this bulb, all right? So you have your work output, okay? So the energy that is actually turning into light is 25. And then you have the total amount of work input you're putting into. So the total energy that you're putting into the light bulb, which is 200 in this case. So if we go 25 divided by 200, and then we times it by 100, okay, we're going to get 12.5. So that's 12.5%, okay, and it's always in percentages here. So only 12.5% of that energy that you're paying for, or your parents are paying for, this is why they always tell you to turn off the lights. That is the reason why it's not very environmental friendly, because you're wasting so much energy on heat. All right, now imagine if you had a light bulb that was 95%. Again, like I said, right, you're wasting so little energy on heat that you could have the output, instead of 200 joules, you could have the output only 30 joules, and it would still be just as bright. Do you understand? I guess you can't answer because this is a pre-recorded video. All right, so I want you to go through all these examples in terms of efficiency. There are some questions here at the bottom. So again, I talked about improving efficiency. It's important because the more efficient something is, the less fuel you have. For the light bulb, we did electricity. But if we could make a car engine use 95% of its gasoline and its fossil fuels to propel it forward rather than coming off as heat, because you know a motor is hot. If we could stop that from happening, then we would not need as much gas, so it would be cheaper for us, because we could have, like, instead of a gas tank being 50 or 40 liters, we could have a gas tank that's 2 liters, and we could get the same distance per fill up as the bigger gasoline tank. It'd be great. Amazing. Where's my cat? So for this option, for an assignment, I want you to go to Energy Skatepark, and that is a simulator that we're going to calculate a little bit of kinetic energy and potential energy here. All right. So if you go onto this site, I'll pull it up right here. If you click on the link in the assignment, it's going to bring you to here. So go through this, follow along with the instructions. It's really fun, and you can have a blast with this. Even do a little extra if you want to, because it's super fun. All right, now I'm going to go to the other assignment that you have. All right, guys, I'm going to go through the second option. So if you don't want to do the simulator, or you don't have access to the internet and in a particular efficient way, in a convenient way, that's what it is, then you can do this assignment, okay? All right, everyone. So if you do not want to do option 1, which is the simulation, you can do sort of a hands-on, arts and crafts construction assignment that you could do with stuff around your house. You'll have 2 options for this particular project. You may either construct a catapult. Think of the medieval things that they tried to get things over giant walls. That's what you're doing here. Or a mousetrap car to demonstrate the conversions of potential energy to kinetic energy. So these can be created using items from around your house. The only thing, be creative, be fun. Like, it doesn't have, not everyone's has to be the same here. So be creative. If you don't have exactly what it says on here, or what you think should be it, improvise, right? Ask your parents, ask me. I'm sure people can help you out. So the requirements for the catapult, what I want it to achieve once you've constructed it, is to launch a tennis ball or something similar about 3 meters away from it into, like, let's say a basket, okay? You'll be allowed to launch it 3 times to accomplish this goal. So if it doesn't work the first time, don't worry about it, right? But try to get it done within 3 times, right? If not, then you'll have to make adjustments to it. So another thing here is the catapult itself must be able to hold the tennis ball by itself without you touching it when it starts. So it's not like where you can, like, hold it down and then release it yourself. You have to make something that holds it for you, or like makes it sit perfectly, so when you release the catapult, it shoots by itself. You can't just hold it. You can't touch it before it launches. That's a no-no. Okay? Record your materials. So this is like any project you think here. For everything you do here, I want you to write down what materials you used, how you constructed the materials. So think of every little detail on how you did it and write it down. So if you used a spoon or something like that, I want you to know how you manipulated that spoon and how you combined it with other objects to make that catapult. Okay, your list must be specific so that I could look at this and I could recreate your catapult to a T. Okay, what I want you to do here is I want you to send a video of your creation in a separate file to me via Google Drive. Via Google Classroom submissions. Okay, so please send a video of it working. That'd be amazing. I want to see your creations. And this is very free-flowing, like whatever way you think you can do it. Use any information you can to make a catapult. Just remember, potential energy. What's the definition of potential energy? Okay, what's the difference of kinetic energy? Okay. Requirements for the mousetrap car. The mousetrap car must be able to travel 3 meters across the tiled floor, so like a kitchen floor. You'll be allowed to run your car 3 times. The mousetrap should be the energy source for your car. So the mousetrap itself, that spring, right, should be what propels the mousetrap, okay? You're not allowed to use batteries, no carbon dioxide cartridges, no any propellant. You're not allowed. You just want that force from the mousetrap to propel the car, okay? No rat traps allowed either. So those are the two options for activities this week. What I want you to do is answer all the questions on the handout that I gave you and do the project as instructed. Okay, if you're doing option 2 with the catapult or the mousetrap, please make a video showing of it working. Alright everyone, that wraps up the first grade 8 video lesson for science, mechanical advantage, work, and efficiency. Now you have a better idea how to calculate it, what it is, and why it's important. So please get those assignments done. Again, only pick one of them and do that. Submit it via Google Classroom, and remember to make a copy of it and submit it. Press the submit button, okay? If you are confused about how to hand it in, please look at the other video I posted on how to submit assignments. It's the same thing, okay? All right, everyone, have a good day and a good week. I'll talk to you sometime this week.